In this video, we're going to talk about several common aspects of manipulating sinusoidal waves, including sine waves and cosine waves. In this case, we'll look at the sine function, but everything we do also applies to the cosine function. And you could easily try it yourself using Desmos. And that's what I'm going to be using is Desmos. We can see right now that this red line is the graph of a sine function. I just put in y equals sine of theta. And what we're going to do is try to do some different things. One thing we'll try is we'll try to vertically shift the sine function. We'll move it up and down. And let's go ahead and turn off this red line. And let's take a look at what it takes to move a sine wave up and down. It should not come as a huge surprise to you that we will add k to the sine of theta in order to move it up and down. Right now k is 0, and so we get a sine wave that looks like one. This is what we would graph if we had to graph a sine wave, a sine function of theta by hand. If we put in various angles in terms of radians, and then this is what we would get as the y values. We would go from 0 to 1, and then down to 0, and then down to -1, and then back up to 0 as we put in 0, pi over 2, pi, 3 pi over 2, and 2 pi. So anyways, let's change the value of k. I'm going to go ahead and move it to 1. And when I do, well, even just as I'm raising it, what happens is the sine wave goes up, and if I bring k down, the sine wave goes down. And this is nothing that's new. This is not new information. When we add or subtract a number from any function that we've looked at in the past, adding the number moves the graph up, and subtracting the number moves the graph down. And so it's true with sine as well as anything else. So I'd like you folks to make a note that that if you have y equals sine of theta plus some number k, making k bigger moves the graph up, and making k smaller moves the graph down. That would be useful. The next thing is, let's go ahead and get rid of that, is this idea of something called amplitude. And this is relatively new for us, but it's a really straightforward concept, so I wanted to discuss it. So what happens with amplitude is this, and I think I'm going to try to lock this in so that it's just, let's see if we can just get it as a step of 1. So we'll see how that works out. So right now we have an amplitude of 1, and what that means is that the distance from the x-axis up to the top of our wave is 1. See how we go 0 here and 2 here? This guy right here is 1. That gives us an amplitude of 1. When the number multiplied times the sine of theta is 1, we say we have an amplitude of 1. If this number changes to a 2, what happens is now the distance from the x-axis to the top of the wave becomes 2. And again, if we go up and we say 3, then all of a sudden the distance from the x-axis to the top of the wave is going to be 3. And again, this applies to a wave that is centered on the x-axis. We would have to figure out our amplitude in a different way if we did a vertical shift on the wave. So anyways, let's do one more. If I change the amplitude to 4, we go all the way from the x-axis to 4 to the top of the wave. All right, so that is amplitude of a wave. And it would really be a shame if I didn't talk to you about some quick practical applications of this. It turns out that when you hear sound like music, when we talk about the volume of the sound, the volume of sound sound is essentially a wave. And when we measure how high the wave goes and how low the wave goes, we actually call that amplitude. And if we have more amplitude, we have higher volume, and if we have less amplitude, we have lower volume. Also, the electricity that comes out of your wall looks a little bit like this. And again, if we get more electricity out of the wall, then we have a higher amplitude, and if we get less electricity out of the wall, we have a lower amplitude. And it turns out here in the United States, in the US, wall voltage looks like this, and it has Usually when we plug into a wall, we say we're getting 120 volts, and it might be interesting to take a quick peek at what that means and how that relates to this sine wave. It turns out that you can actually see what wall voltage looks like by using a device like this. This guy is known as an oscilloscope. And you actually take a couple of wires and put it into the jack in the wall, and you can actually see the voltage. And it turns out that that when you're talking about US wall voltage of 120 volts AC, known as alternating current, in other words, it alternates up and down, positive and negative, we have 120 volts AC actually gives us a peak voltage of about 170, approximately 170. And so what that means is that's the amplitude. If we go from the x-axis in measuring the wall voltage up to the top, on this scale we have 50 volts per division, and this is 1 division, 2 divisions, 3 divisions, 4 divisions. So this will be 50 volts, 100, 150, 200. The peak is at about 170, in this case 172 volts. So with that, we can be sure that when you plug something in the wall, you're getting at least 120 volts. So amplitude of wall voltage, if we measure it, it's about 170, 172 volts. And that's how that relates to the sine and amplitude. Okay. Also, the same is true for sound and volume. And I don't want to take much more time in this video, so if you don't mind, I'm going to move on. Another thing that I'd like to talk to you about is the idea of the period of a sine function. And so what we're talking about is how long does it take to complete one entire cycle? In other words, here we go up and then down. And then what happens is when we finally get back to the x-axis here, our cycle is repeating. This part right here, we've seen it before. It's right over here, okay? And so what happens is we're interested to know is what is the length from here over to here. In other words, one complete cycle of our sine wave. And it turns out the thing that affects the period of the wave is something multiplied times theta. Now in this case we have 1 times theta, and when we do for this sine wave, we get one complete period or cycle that goes from 0 to 2 pi. In other words, all the way around the unit circle. If I change this to 2, you get a very interesting result. All of a sudden one complete cycle goes from 0 to pi. In other words, by multiplying by 2 the angle here, we cut the period in half. Now the period is only 0 to pi instead of 0 to 2 pi. And we'll try it again. I'll go up to 4. And again, now I've cut the period down by 1/4. So whatever b is, if we put, basically that cuts down our period from 2 pi into 2 pi divided by whatever that number is. So the way that we think of the period of a sine function or a cosine function is that if we take 2 pi and divide it by the number multiplied times the angle, we get the period. So in this case, the period goes from 0 to pi over 2, and we would get that by dividing 2 pi by 4, and sure enough we would get pi over 2 is the length of the period. Alright, exciting stuff. So that's the explanation of the period, and I'd like to you to try to write that down and try to paraphrase in the best way that you can. Now there's one last thing. To me, the vertical shift and the amplitude and the period are several things that are very important for you to know about sine and cosine functions, and they're also relatively simple. The horizontal phase shift is a little bit trickier, but I'll at least introduce you to the concept. So the way this works is our good old friend h. Remember, k moves us up and down, h moves us from side to side in any function. Well, pretend like theta is x minus h. Sure enough, it's going to shift the thing from side to side. So I'm going to put h back to 0. And there we go, our good old sine function. And then I'm going to go ahead and increase h. And as I do, as long as it's theta minus h, it moves the sine wave to the right. And if I decrease h, it moves the sine wave to the left. All right, I at least wanted to get that mention in. Now, one thing that's kind of interesting, I will say this, there's a practical application of this horizontal, also known as phase shift. And that is what happens is if I shift the sine wave enough, what you'll notice is that we get just the same thing we started with. In other words, if we shift the whole sine wave by enough, then all of a sudden we're back to what we had at the beginning. Notice this just looks like an ordinary sine wave, and I've shifted about 6.3, or also known as approximately 2 pi. And so if I move the whole sine wave 2 pi, sure enough, I get exactly the same thing. Now here's a really interesting thing. If I shift by about 3.2, approximately pi, what happens is I get an exact inverse of the sine wave. Let's see the original sine wave so you can see it. Notice that the new sine wave that was shifted pi, it goes down and then up, and the old sine wave that we started with goes up and then down. And they're exactly the opposite of each other. And this has a very interesting practical application in the real world. It turns out that if you've ever heard of something called noise canceling headphones, the way it works is this, is that in what we have is something like this. Noise or sound looks like a wave like this. And it turns out that if you have the right electronics, and the electronics has a microphone, and the microphone hears this sound, and then the electronics phase shifts this sound wave like this. It turns out that this inverse wave cancels the initial wave. These two guys cancel each other and the sound goes away entirely. This is the math behind the science of noise canceling headphones. Now, even if you don't understand that perfectly, that's fine. I just wanted to give you a heads up that this math, although it might seem pretty intense, it does have some actually pretty cool and practical applications.